Hello, welcome to Quantities in Chemistry. First video, and it's going to be about the mole. Now this is all based on chapter 3 in your chemistry textbook, so if you want more information, go have a look at chapter 3. Now some of you may have already heard about the mole, so what is the mole? Ah, there it is. That's a mole. No, that's not the mole. That's a mole. Seriously though? Alright, chemists use a unit called the mole to count atoms, ions and molecules. And chemists always want to count atoms, ions and molecules because they want to know what's happening in reactions and how much to use of something or something else and whether it's going to get used up or whether there's going to be too much of it. And chemists soon realize that in terms of the atoms and ions and molecules that they're talking about, the numbers are massive because they're so small, and the amounts that we're dealing with, the numbers are just a bit too much to handle, and therefore there was an easier way. And just like we might say a dozen eggs, meaning 12 eggs, chemists say a mole, and what they mean is the mole is 6.02 times by 10 to the 23. And so when they say a mole, that's the number they represent. And it is a very large number. But the world is made of many more things than that number. We'll talk about how big that number is, but in the grand scheme of things in the universe, it's not a very big number. But it makes life a lot easier for chemists to use the mole concept. So how is this number defined? Well, it was defined as the amount of a substance that contains as many particles, be they atoms, ions or molecules or anything else, as there are atoms in exactly 12 grams of pure carbon-12 isotope. So if you weigh out exactly 12 grams of carbon-12, this is how many atoms there are. And so we can say, we can use that number, and that's the definition of number, and we can use that number to describe anything. So when we write it fully, that's how big it is. And so it's a very big number. How big is it? Oh, I needed to remember. This is Avogadro. Now that's a caricature of him, so it's not actually a portrait. So it's been exaggerated a little bit, and I think that's pretty much the only image that's available of him, because it was a long time ago. Now this is called Avogadro's number because he was the one that first formulated it, and that's Avogadro's, obviously. So how big is a mole? Well, if you had 1 mole of marshmallows, that would be enough marshmallows to make a layer 19 kilometers thick, covering the entire surface of the earth. So imagine everywhere on the earth covered by 19 kilometers of marshmallows. That's a lot of marshmallows. 1 mole of marble spread uniformly across the surface of the earth would produce a layer 60 kilometers thick. Now that's over the surface of the continents, so 60 kilometers. 1 mole of blood cells, now you think blood cells are pretty small. If you had 1 mole of blood cells, and you must have a lot of blood cells in your body, 1 mole of blood cells would be more than the total number of blood cells found in every human on the earth. So that's a lot of blood cells. 1 mole of sheets of paper, that's something we can understand, would form 1,000,000 stacks from the surface of the earth, all that would pass the sun. So you'd have 1,000,000 stacks of paper, and they'd all extend further than the sun. And if we had a mole of 10-cent coins, and if we could distribute them to all living people in the world so that they could spend $1 million per hour, every hour, day and night, for the rest of their lives. That's a lot of coins. And finally, if you are able to count at the rate of 1 million numbers a second, so 1 million, 2 million, 3 million, so it would take you about 20 billion years to count out 1 mole. And seeing that the universe is not that old, you can't do it. Now the mole concept. So the mole concept is it enables us to count particles present in any substance. To find the mass of 1 mole of an element, all we have to do is add G, as in the unit grams, to the relative atomic mass of that element. So here are some examples of 1 mole of mercury, zinc, silicon, aluminium, sulfur and bromine. That means each of these amounts in these beakers contains 6.02 times by 10 to the 23 particles of either mercury, zinc, silicon, aluminium, sulfur or bromine. So each of these is 1 mole. So we're going to throw these numbers around and this terminology around a little bit. So each of those contains Avogadro's number of atoms. Now, where do you get the relative atomic masses of these things from? Well, you can get it from your periodic table on your information sheet. This number here and here and here and here are all the relative atomic masses of these substances. So if I wanted 1 mole of lithium, I would weigh out 6.941 grams of lithium, and that would contain Avogadro's number of lithium atoms. Whereas if I wanted 1 mole of potassium, I would weigh out 39.1 grams of potassium. Now there's also a table on your information sheet on one of the pages where all the elements are listed alphabetically, and you have the relative atomic masses. Now notice that some of them have 2 decimal places, 1 decimal place. So from now on we're going to use these decimal places fairly much so. Previously, whenever we've been using the masses or how much an atom weighs, we've been rounding up and down, and it's been fairly easy to do that. But now we're going to start using, particularly in the next section when we do stoichiometry, the decimal places. So just look out for that. Some more examples of moles. Now previously we had moles of elements, but we can have moles of compounds. For example, 1 mole of water, if you weighed out 18 grams of water, that would be 1 mole of water molecules. There we have a mole of copper sulfate, 250 grams, 1 mole of iron, 56 grams, aluminium, 27 grams, sulfur, 32 grams, calcium carbonate, which is an ionic compound, 100 grams. Now how do we know these masses to weigh out? Well, we're going to work that out in this video. So the term that we're going to use now is the molar mass, sometimes given the capital M in chemistry equations. Now the molar mass of an element is the mass of 1 mole of that element, and its units are grams per mole, the -1 meaning per mole. For example, the molar mass of carbon atoms equals the mass of 1 mole of carbon atoms, which equals 12 grams per mole. So what is the molar mass of carbon? It's 12 grams per mole. So if you have 12 grams of carbon, it contains 6.02 times by 10 to the 23 atoms, because 1 mole must include that number of particles, Avogadro's number of atoms. Now notice here that we've lost the E. That's because we're talking about 1 mole in terms of concentration, not in terms of number. The molar mass of oxygen atoms equals the mass of 1 mole, and mole is the number, so when we have this number of atoms of oxygen atoms is 16 grams. And you can look on your periodic table and you'd see that carbon is 12 and oxygen is 16. Now in this case they've got rid of the decimal places. So if you have 16 grams of oxygen, you have Avogadro's number of atoms of oxygen. So what about compounds and molar masses? How do you do that? The molar mass of a compound is the mass of 1 mole of that compound. So it is found by adding together all the relative atomic masses of the atoms in its formula and adding grams per mole as the unit. So the molar mass of a substance, we add together all the relative atomic masses and we add grams per mole. So what is the molar mass of water molecules? Well, the mass of 1 mole of water molecules equals 18 grams per mole. So if we have 18 grams of water, we contain 1 mole, or Avogadro's molecules of water. Now where does this 18 come from? Well, the formula is H2O, and if we look up our tables, hydrogen is 1, so we need 2 times 1, and oxygen is 16, so 2 times 1 plus 16 equals 18. So we added up the relative atomic masses. So what about chlorine gas? Well, chlorine gas is Cl2, so that will be 71 grams, and if we weigh out 71 grams of chlorine gas, it contains 6.02 times 10 to the 23 molecules of chlorine. How do we get the 71? Well, if you look up chlorine, it has a mass of 35.5. There's 2 of them, so that's the mass of 1 atom. There's 2 atoms in the formula, so we times it by 2. What about ionic compounds? Well, to work out the molar mass of ionic compounds, we add together the relative atomic masses of each atom in the formula. And sometimes the symbol capital M with an R is used for this. For example, copper sulfate. So copper sulfate contains 1 copper, 1 sulfur and 4 oxygens. So we need the relative atomic mass of copper, relative atomic mass of sulfur plus 4 times the relative atomic mass of oxygens. So that's where we go. So this 4 here is important because it gives us 4 oxygens. And copper is 63.5, sulfur is 32.1, and oxygen 16 times by 4 gives us 159.6. Therefore the molar mass of copper sulfate is 159.6 grams per mole. In the next video we're going to learn how to change moles to number of particles and number of particles to moles. See ya.